There we go. There we go.
Oh, you're now seeing it.
It may take a moment, but it is definitely streaming now.
Yeah, I can read what the quality looking at the internet.
At the moment, it's still streaming. Yeah, live.
Okay, we're live.
Hold on, let's just check. Yeah, I think it's okay.
Okay, we're on.
Yeah.
Stream's active.
Okay, right, where were we? The STL, containers and algorithms decoupled. So what are iterators? Why do we care? Iterators are the glue that binds together these things called containers and these things called algorithms. That's how they talk to each other. So containers provide iterators and algorithms consume iterators. So an iterator is the interface between containers and algorithms. So to give you an example, standard vector is a container. We get an iterator to it. We'll go into this in a bit more detail in a minute. We get an iterator to the beginning of the vector. We get an iterator to the end of the vector. And then we sort. We pass these iterators to the standard algorithm. The algorithm doesn't know about standard vector. It just works on the iterators.
If it is also because it can be in inter, size, or different kind of different types? Or?
Yes, we'll get on to exactly what type it is in a minute.
Okay.
Or a few minutes anyway. Auto's very handy because it lets you not really care about what the actual iterator type is. But this last point is quite important. There isn't, it used to be a class called standard iterator, but there is no one iterator class. An iterator is what's called a concept. So if a type matches the requirements of an iterator, then it's an iterator. So it's what they call duck typing. Right? So in order to define an iterator, there's a whole bunch of standardese that tells you exactly what an iterator must do. And if you write a class that does all the things, that's what's called a concept. Now, today in C++, we have no notion of concepts in the language itself. The standard uses these things called concepts. We have no language construct called a concept. That's hopefully going to change in C++ 20, and there'll be actual support for being able to test concepts. So at the moment, as I said, in order to act as an iterator, your type has to meet all these requirements. What happens if you try and use a type that doesn't meet these requirements is that you get a horrendous mess of template errors deep in the implementation of standard sort. So if you try and use standard sort on a list, which you know how to do, then you will get, I think last time I looked on Clang, you get something like 300 lines of error messages. So hopefully that's going to go away in C++ 20. But I'll talk a bit more about that in a moment. So what is an iterator? I'll just say an iterator is a concept. But what can we do with iterators? What are the requirements? Well, conceptually, I suppose, an iterator. And the simple answer is an index into some set, into some collection. Okay, so it knows which collection it belongs to, and it's just an index into that set. It's a bit of trivia. In the original version of the STL, Stefanov called them linear coordinates, and the standard committee persuaded them to change this term to iterator. So there we are. A slightly more complicated answer is that iterators are a generalization of pointers. So if you think about a C array, a raw language array, you can have pointers to the elements, and you can perform operations on that pointer. You can make it point to the next element. You can dereference it to access the element. And iterators are a sort of generalization of that. Oh, and that's just what I said. By the way, I can't actually see what's coming up or see my notes on it. I can only see what's on the screen, so I have to make it up as I go along. So A raw pointer can act as an iterator into a C array, and just like that, something which meets the iterator requirements points to an element of some other container type, be it a linked list or a hash map or whatever it may be. Does all make sense? All right, so iterator fundamentals. What are the very basic things we can do with iterators? So I've just said an iterator points to an element in the collection. First thing is we want iterators to be cheap to construct. That means iterators shouldn't, for example, allocate memory on the heap. Formally, they say iterators should be constructible in constant time. So constructing an iterator shouldn't depend on the number of elements that you've got in your collection, for example. And the same thing, cheaply copyable. So the standard library copies iterators all over the place. So we want iterator copies to be as quick and as fast and as cheap as possible. Ideally, you know, the same cost as copying a pointer or a couple of pointers.
You've been complimented for your English accent.
Oh, right, thank you. So one of the fundamental things we can do with an iterator is we can dereference it. We can dereference it to get access to the element that it points to. And we do that by saying, if we have an iterator called iter, we'd say star iter. So just as you use star to dereference a pointer, so iterators are required to have an overloaded unary operator star, a dereference operator, in order to be able to access the elements. You're about to say something.
What if I were to dereference end?
Patience, man, patience. The other thing we can do is we can advance an iterator to point to the next element of the collection. We do that by saying ++ iter. There's also a wrapper function in the standard library called standard advance, and there's another one called standard next, which can do these things for you. But yes, we use ++ iter. So this syntax, star iter, ++ iter, it all comes from pointers. So this is the pointer syntax. This is how you manipulate your pointers. So we're using operator overloading to add these operators to some class which we want to meet the iterator requirements. The other thing we need to be able to do is we need to be able to compare iterators for equality. And two iterators are equal if they point to the same element in the same collection. And we have to be able to say, does iterator 1 equal iterator 2, and the converse is iterator 1 not equal to iterator 2. Sorry. And these are the most basic operations. This is far from the complete list. CPP reference is amazing and has all the gory details. And in fact, you're going to be looking at the gory details later because you're going to be implementing an iterator. So that will be a challenge, I'll tell you now. So just a brief example, the absolute fundamental operations on the iterator. Declare a vector. It'll work. We create an iterator called iter1, which points to the beginning of the vector, first element of the vector. And we can copy construct the iterator. So now we're creating another iterator, which is a copy of the first one. So now these two iterators both point to the same element. And we can compare them for equality, so we can assert that the two iterators are equal. The two iterators are equal because they point to the same element in the same collection. We'll advance one of the iterators. And now the two are hopefully no longer equal. And if we dereference it, I could have said also here, but we know we're going to get an int because the value type of this container is int. So we dereference the first one, dereference the second one. Now if we print both of them, we're going to get 2, 1. That's because we've advanced it to 1, so that it's moved from pointing to this element to pointing to this element. So when we dereference it, we get 2. Iterator 2, we haven't advanced, so it still points to that one. So when we dereference it, we get 1. So when we print the final line, we get 2, 1. The key idea here, really, if you're interested in that, iterators have value semantics. Copies are independent, mostly. Sort of caveat for input iterators, but we'll get to that later. So does that make sense?
Yes.
If anything doesn't, then you need to shout at me, because otherwise I'm just going to plow on.
So essentially, if I have an iterator to an object, I dereference the iterator. That object, if I modify that, I'm modifying it inside the actual vector. I'm not just modifying a copy that's thrown away.
Yes, absolutely.
So if you have any questions, ask. Raise a hand and ask. I'm relying any messages from the online people, but this is for you. If something is amiss, don't worry. I'm one of the idiots who doesn't know everything, and I ask. Yeah, so don't be shy. You're not alone.
Well, let me try one. Maybe you already told before I came a difference between iterator and pointer.
A pointer to a member of an array anyway is an iterator.
Okay.
Yeah.
No difference in performances or
No, at all.
Okay, cool.
A pointer to an element of an array is a valid iterator.
Okay.
But so from a language perspective, is that the right description of it?
Yes. So it meets the requirements
Of an iterator?
of an iterator type, yes.
Right.
Use a range-based for it, but I want it.
Yeah.
It is then.
Or on a C array anyway, because you pass the connection. Right, iterators and ranges. So we saw an example of this before when we called standard sort. Iterators are generally used in pairs. So we have an iterator which points to the start of the range, and an iterator which points to the end of the range. So almost all the standard algorithms operate in pairs. Bit of terminology, we refer to this pair of iterators as a range. So as I said, the first iterator points to the first element in the range. I lied to you, the second iterator points to one place past the end of the range, which is really important. Right, so it's what's called a half-open range in mathematics. So it includes the first element, but it does not include the last one. That's if you remember nothing else today, remember that. It is an error to dereference the past the end iterator. So Ollie just asked this a second ago. If you call vec.end and you get an iterator and then you try to dereference that iterator, that's what's called undefined behavior. It's not allowed. You might get away with it. Your program might crash, might format a hard drive, whatever. You're not allowed to do it.
Isn't that called a feature?
Demons flying out of your nose.
Yeah.
Nasal demons.
Sorry, can you just explain with the range, if you're saying you have, I don't know, 10 things in your array, and then you say count the first one, the last one would be index 10, but you're saying it counts past that.
It's a lot easier. I draw it on the board. The reason I'm drawing it on the board is because I'm rubbish at drawing things on Keynote. So this is an array with 4 elements. So when we call begin, it returns an iterator which points to its first element. When we call end, it gives us an iterator which points to nothing. It points to this imaginary space at the end of the array.
And when I try to dereference it, I don't get an error. I get the rubbish which would be in the RAM or whatever.
Or you might crash, or you yes. It's an error in your program, which usually unfortunately, because C++ is efficient, the compiler isn't going to give you an error message, and yes, it might work correctly, it might crash.
Most likely not.
Most likely you're just going to get junk.
Okay.
Whatever happened to be next in memory, which is somewhat unfortunate.
So you could assume, let's say, if I don't get 4, so if return is not equal to 4, then I pass the iterator.
No.
If not, so if it's 4, yes, or the next one, that's a valid iterator. I didn't pass through the last one. Am I correct? Okay, okay, you can check by, let's say, I'm not sure exactly how many was the last one, yes? So if I say, okay, the first one is 0, then I know if the next one is equal 1, I'm not at the end. True. So if the next one is not equal to, is equal to 2, then I'm still not at the end. But eventually I go to the point where I say, if the next one is, let's say, is equal 4, let's say, and I get something else, that means I'm at the end. Am I correct?
Not quite. So that's not how we use iterators. I'll give you an example. Probably, I think it's on the next slide. Of how you go through the range. Okay. The key point here is end. When you call the end method on a container, it gives you one past the end of one past the last element. Okay, so a range in C++ terms is half open. It includes the first one, it does not include the last one.
Why is it called half open?
It's a term from mathematics, because you have open sets and closed sets, and if it includes the end values, both end values, then it's a closed set. If it doesn't include the end values, it's an open set. If it includes one but not the other, it's half open. It's a mathematics term, but just kind of imported into computer science.
So when you add new additional element into that vector,
Yeah.
You have to redeclare your end again?
Yes, you do.
Okay.
Yeah, it's called Iterator Invalidation. And it's so important, I'm going to spend about 5 minutes talking about it. Okay, any more questions? I'm going to leave that on the whiteboard because I might point to it again. I'll let Ollie play with it. Yeah. This is just what I said. We can obtain an iterator of the starter container by calling its .begin method. We can obtain an iterator of one past the end by calling corresponding .end. And there are also these in C++ 11. There are added these non-member functions, free functions, standard begin and standard end. If you call standard begin on a vector, say, all it will do is call vec.begin for you. So you say, what's the point of that? It's because C arrays, raw language arrays, don't have member functions.
There's another reason. Constant.
No, begin has a constant array.
I mean, if you call .begin just from the instance, that will fail if it's const, whereas...
No, right. You return your constant array. Absolutely.
Carry on. Today I learned something.
Yeah. So sorry, this would be for me a way to know the length of an array. I do begin, and minus begin, and then I divide it for the size of a cell. And
that is a way to do it for. It only works on what are called random access iterators. Okay. We'll get onto exactly what that means. There's even a function in the standard library that does that for you. It's called standard distance, and you pass it to iterators, and it will tell you how many times you have to advance one iterator till you reach the second one. So, yes, that function is in the standard library already for you. It's called standard distance. So yes, there's not a great deal of advantage. If you know what container type you're working with, there's no real advantage to using standard begin and standard end. I tend to mix and match them. The free versions are good in really, if you're writing template code, writing generic code where you don't know the array type, then begin and end are useful.
Kate Gregory is a very big friend of the beginning bracket and brackets instead of the dots.
Yeah, I guess there's no reason not to, so I guess, yeah, get in the habit of doing it. She knows better than me, so Kate Gregory says to do it, then listen. Oh, we've got lots on this slide, we've got tiny text. So, to work our way through a container, what we will typically do, as I said, take a pair of iterators, and we advance the first one until it is equal to the end value, and then we know we're done. So if we run over here again, we imagine we call ++ on this, then it will move so it points to element 1, and then again to 2, and then again to 3, and then one more, we call ++ each time. Eventually, it will be pointing to this space at the end, and at that point, we know that the iterator, because we can compare iterators for equality, we say, are you equal to end? And if you are, we know we're done.
How do we know what end is? Because that could be garbage, isn't it? And we don't know what the values are.
You don't. This doesn't have a defined value. So, got to think, an iterator just points to, at the sort of the lowest level, when we're talking about arrays, it literally just points to some bytes at the end.
Yeah.
So you can't dereference this, you can't look at what it points to, but you can say, is the address that you're looking at the same as this address?
Maybe another way to explain it is, so if you were implementing an iterator, which you'll do later, you could theoretically say that, okay, the iterator's end is internally going to have value -1, and your iterator class will then just have it operate equals, have to, if it's -1, that's with the special end. So your end doesn't, if you're using, like, say, contiguous memory, right, where it's all together, then you could just say your end is the memory address past the actual final object, right? So you can just use that memory address. If it was something more complex, then you could just say, yeah, we'll use a magic number to represent the end, or, magic case.
So you say, if you use a continuous memory, this kind of logic works even if you store something not continuously?
Well, the thing is that the thing is basically just implementing various operators in a class to do the iteration. So technically, you just have a Boolean called isEnd. So when, say you implement your own version of vector or whatever it is, when it returns the end iterator object, it instantiates that object and sets its end Boolean to true. Generally, you probably wouldn't need to do that, for optimization purposes, wouldn't bother, but you could. You could have a special field where it knows it's the end one, or you could implement by inheritance, or, there's a million ways to do it.
So we can talk about arrays, but if you think about a linked list, those who've done computer programming and need to sit in those lessons where you write a linked list. A linked list, you have a node that contains a pointer to the next node, contains a pointer to the next node, and eventually the last node in the chain usually has null, and that's how you know you've got to the end. So if we were implementing an iterator for that, begin would return some sort of, would point to the first element, and end would point to this null pointer thing on the end. So that's how you would know that you had got to the end of the array.
Can I ask a question? Probably very stupid, but the null pointer, yes, it's like unidentified, it's not like a specific character, so it could be like garbage. Can it be the situation where like a random memory read will give you something which is, no?
So null pointer is a special value that, unless you're writing sort of Linux kernel code, no memory address will ever be 0. So the only way you can get a null pointer is if you specifically set a pointer to equal to a special value. Okay, so just to show you how we use iterators to traverse through a range. There's a standard library algorithm called count. This is an almost correct version of count. The return types are different, but because it's complicated. So first thing you notice is that we're templated on the iterator type and this value type C. We take our iterators by value, that is, we copy them. We copy the iterators when they come into the function. We've got a question? Oh. We copy the iterators when they come into the function. That means we can alter the iterators, we can manipulate them, and we don't affect the calling code. They're value types. So we initialize this variable counter, and now this is the key line. You see, while first is not equal to last. So remember, we can compare iterators to see whether they point to the same elements. We presume we can pass begin and end. So while first is not equal to last, we do something. We say if star first, so if the value that first points to is equal to the value we've been given, then we increment our counter. And then we increment the iterator. And then the loop restarts. And now first points to the next element. So what's important to note here is that we're going to keep excuse me. We're going to keep incrementing this first iterator. And then as soon as it's equal to the last one, we exit the loop. So we never execute the loop body. We never dereference the end pointer. So this, while first is not equal to last, do something and then increment the iterator is really, really common. That's how an awful lot of these standard library algorithms are implemented. And then just for the sake of this, to complete it, we return the counter. Show you how to use it. We have a vector we call count with vec.begin and vec.end, or I could have used standard begin vec, standard end vec, and we're looking for the value 2. And it returns us the number of 2s, which hopefully it will count 3 of them.
And we use the size as a type of a result to be of a function to be safe.
Yeah, so the actual standard library implementation uses a type. Uses the iterator difference type, but that's the sort of detail I didn't really want to go into now. But yes, size T is safe for this, you know. Yeah. Realistically, on any computer today, it's going to be an unsigned 64-bit integer, so yeah, you're never going to overflow it realistically.
Okay. Because size, if I remember correctly, depends from implementation.
Yes. Okay. Yeah. So, but basically, on a 32-bit machine, it's going to be an unsigned 32-bit value, and on a 64-bit machine, it'll be. Yeah,
I had a discussion last week, I think, about the difference between a long and int and so on size, where it's distributed. And
yeah. So long is a bit unfortunate because on Microsoft, even if you're on a 64-bit platform, long is still 32 bits. So yeah, longs, avoid using long, basically. Jet taking off nearby. Okay, range for loops. So you've probably seen these because I've used them in examples. I'm sure you've used them in any code you've done for this class. There's this new fangled thing in C++ 11. It's called a range for loop. And you can use that via any type that meets these container requirements. So just as I said, iterator is a concept, and you can implement a type which meets the iterator requirements. So the standard library defines some container requirements, and again, the details of it are quite in-depth, but the sort of short version is something which has begin and end methods, or something on which we can call standard begin and standard end, which return things that meet the iterator requirements. And if we have one of these container things, we can use it in a range-based for loop. So in here, what this is doing is it's calling standard begin of the vector, getting the iterator, dereferencing it, and then putting the result in this variable I. And it's doing that again and again until it reaches the end value. So just as I showed you with while first not equal to last, that's basically what the compiler is doing in this for loop.
In terms of performance, it's the same, but it's just a synthetic sugar.
Yes.
Okay.
Yeah. Okay, iterator types. So, as I said, there's no one iterator class. Every container implements its own iterator type. So vector iterator is different to a list iterator, different to an unordered map iterator, different to a standard deck iterator, and so on for all the different container classes. All the containers have this nested type, which is colon iterator, so has a nested type called an iterator. So if you really want to, you can say type name standard vector int colon iterator iter. So you are asking, I think, how we get the name of this type, and it's like this, which I think you'll agree is really ugly, but it's what we have to do in C++ 98.
Wow.
But magically, wonderfully, we got auto in C++ 11, so you almost never have to type this hideousness anymore, which is great. But I think it was most of the reason why auto was put in there. Const Iterators. Right, so do you remember, well, probably only two of you were there at the time, we had a long session, we talked about const pointers versus pointers to const. We got ourselves in, we had lots of fun trying to decode these types, right? There's a concept called a const iterator. So a const iterator is something that provides read-only access to the container's elements. So if we have a const standard vector, then when we call begin on it, what it returns us is a const iterator. And a const iterator in general has a different type from the mutable iterator, the standard iterator. But it still, obviously, it still meets the iterator requirements. Or you can call this cbegin and cend method. So if you don't have a const iterator, but you don't need to mutate it, you can call cbegin and cend. It'll give you a const iterator, which is a bit safer because you know you can't accidentally overwrite any of the vector's values via a const iterator. And yeah, see, I don't know why they went to C++ 11, but anyway, C++ 14, there are these free function overloads as well. A non-const iterator can be converted to its equivalent to const iterator type, but not vice versa.
You can copy the value, assuming that you have the value from a const.
You can copy the value.
You cannot convert a const into a non-const, but no. you can still transfer the value to a non-const.
Yes, I think you can dereference a const iterator and get a copy of the value, and then you can copy that value and assign it back into the container versus via the mutable iterator. What you can't do is initialize, in general, is initialize a mutable iterator to say, point to this same element, but in a way so that I can mutate it. Okay. And just to be really confusing, a const iterator, when we talk about const iterators, we mean that the element that we point to is the thing that's treated as const. So we can't mutate the element that we point to via this iterator. So it's like the difference between const pointers and pointers to const. We can have an iterator, a const iterator, which is one through which we cannot mutate the values in the container. You can also have an iterator that is declared const, and then we can't call any mutating member functions. We can't advance it. It's a bit complicated. Const pointers and pointers to const is one of the more fun aspects of C and C++, and it carries over into iterators as well. Could have had another bullet point. Use const iterators when you can. So if you are calling an algorithm which you don't want to or can't mutate the thing that is pointing to, pass cBegin and call cBegin and cEnd. Get into the habit of using cBegin and cEnd unless you specifically want to mutate the container, in which case call begin and end. Make sense? No, it's excellent. Okay, so this was talking about iterator invalidation. We're doing for time, not bad. So iterators can become invalidated. So an iterator points to an element of that container. But what can happen is if that container's internal structure changes, the thing we were pointing to goes away. And when that happens, the iterator is said to be invalidated or dangling. And dangling iterators are, unfortunately, a frequent source of bugs. And the compiler rarely does much to help you. You can use static analyzers, do quite a lot of good on this, I think. You've used them more than me.
Yeah,
you don't have dangling iterators anyway, so you've never seen it. Right?
No. Never have this kind of bug. I never write bugs, obviously. No, sanitizers and static analyzers are very helpful. Yeah.
So if we have a dangling iterator, what do? We can't dereference it because it no longer points to anything valid. It points to a bit of junk memory. So we can't dereference it. We can't even advance it because we don't know where to go next. So the only things we can safely do are either destroy it, let it fall out of scope, or to reinitialize it by assignments. So if you remember we were talking about move from types, it's kind of the same situation as a move from type. The only safe things to do, destroy it or reinitialize it. So the best example, the one that trips people up all the time, is if you call pushback on a standard vector. So pushback adds a value to the end of the vector. When the vector is full, it needs to reallocate its internal data structures, and what it does is it internally creates a new array, moves all the values from the old array into the new array, and deletes the old array. That's what it does internally. But you, as a user, can't really tell when pushback is going to do that and when it's not. It depends on the internal implementation.
You're going to be in place and in place back as well.
Yes, yeah. So that means that you've got to treat any call to push back as potentially invalidating all of your iterators. Fortunately, the standard library goes into great detail about exactly which member functions potentially invalidate iterators. So yes, I'm sure if you go to CPP reference, it will tell you that in place back potentially invalidates. One thing you can be fairly sure of, or absolutely sure of, is that const member functions won't invalidate. Calling a const member function on a container won't invalidate any iterators because it can't mutate the container. So you can be safe with any member function that's marked const. It's the mutable ones you've got to worry about. Even then, not all of them will invalidate. If you have a list, for example, you can safely chuck things on the back of it and it won't invalidate any iterators. If you do find yourself in this situation, using vector and pushback, quite a useful thing to do is, so let's say you're in a situation where you want to store a bunch of iterators to various elements in a vector, and you're worried that as you add more elements to the vector, you're going to invalidate all of your stored iterators. What you can do is actually just store an index to a particular element number, right, which sort of avoids this, because as long as you don't shrink the vector, there's always going to be an element at position 4, say.
Sorry, just a question. What if this vector reassigns the old memory to create a bigger one?
Yeah.
And sort of destroys the previous memory location? That wouldn't work then.
Yes, because if you say, vector, please give me, with the square brackets operator, if you say, please give me the element at position 4, it's going to give you whatever is at position 4 now. It's going to look, because it's going to use its new data structure. What won't work is if you try to store a reference to the element of position 4 or a pointer to the element of position 4, that's going to invalidate that as well. So yes, iterator invalidation is something that you have to worry about. These are some of the perils we have from using a language with no safety features, I guess. So
check if the iterator is still valid. Is always safer to check if it is within the beginning and end?
No.
Okay.
Oh wait, no. So once it's invalidated, you literally can't do anything with it other than destroy it or reinitialize it by saying iterator equals standard begin or something.
To give an example of this, if you add an element, an implementation could potentially sort of reuse that memory area, but it might shift bound. So you could just be pointing to a random element inside it, which would probably still dereference, probably, but it's UB, it's undefined behavior, it's not something you can rely on. So
what they wanted to know is there are some implementation which do recycling. Instead of creating a new array, new vector somewhere else, in this case, you can also recycle the same vector.
Internally, it's very unlikely to be able to do that, which is also why generally for performance, if you're going to use a vector, you should use the reserve member function to tell it how many things you're going to stick in it, so that it doesn't end up reallocating. So if I want to stick 1,000 things in it, if I don't call reserve, it's going to keep on reallocating. Do what?
Do doubling in size.
Yeah.
So, okay. And the other way around.
It won't shrink actually. So if I throw 1,000 elements into a vector, and then I dump 500, that memory just sits there empty.
The capacity will still be.
Yeah. The only.
Okay.
You have to call there's a method called
to allocate the memory and give you something.
No, it won't deallocate. You can call shrink to fit in C++ 11, and that will shrink it. But you have to do it yourself.
Oh, it does dot clear.
Oh, dot clear will wipe it out, won't it? You have to wipe everything then. Or make a new vector and stick the stuff there.
But clear is quite resource demanding. Am I correct?
I mean, it's as demanding as it is to destroy the type. So you have I have 1,000 integers. Since they're trivially destructible, no, it can just throw the memory away. If it's a complex class, so it's a vector on some class with an actual destructor that actually runs code, then yes, for every element it's got to call the destructor and execute that. But for trivially destructible types, no, it's gone. Okay.
Refreshments.
It does not use capacity.
Clear doesn't. No, do it used to when they specify in 11, but it doesn't.
No, it doesn't.
All right. So this is just a bit of a side note. That there's currently a lot of work ongoing to do with ranges and iterators, and kind of not really changing or not reinventing the way this works, but to kind of formalize it a bit more than it has been. And it will allow you to directly use ranges. So we said an iterator pair specifies this imaginary thing called a range. So there's work going on to actually formalize this notion of a range. So you'd be able to say kind of vector, and rather than having to say vector begin and vector end, you just pass the vector. which would be nice. This, by the way, this standard ranges sort, there's no guarantee that's what it's going to be. There was literally a committee meeting that finished on Friday, and as of Friday, that's what it is, but it might not be in 2 years' time. So there's much more to this ranges proposal as well. This is just the very tip of the iceberg. Ranges will be absolutely brilliant. So hopefully, fingers crossed, they'll be in C++20, which is the next version. No guarantee, but fingers crossed. In the meantime, there's this library called Range v3, which is written by a guy called Eric Niebler, and Casey Carter is the other person who does a lot of work on it, and it's really good. Unfortunately, it doesn't work with the Microsoft compiler at the moment, but if you use Clang or GCC, highly recommend Range v3, and there's a link to it there as well.
Prop compiler.
Oh, Justin was talking to me, but he's not. Never mind. Do you guys use Range v3? No? No. Well, you should, because it's great.
I mean, I don't have that much big of a deal with problem with iterators, but I guess you might feel more at home on the ranges. All right, I'm gone.
All right.
That's a brutal exit.
Iterator categories. So far we've only talked about the very basic things you can do with Iterator. That is, dereference them, advance them, compare them for equality. There are more advanced iterators. Those are the very basic ones. Sorry, there's a lot on this slide, and it's made the text tiny.
My opinion is happy that you do it.
But there are actually the family, 5 kinds of iterators. And they form a hierarchy. So we have input iterators and output iterators, are the lowest level, least powerful ones. Then we have forward iterators. A bidirectional iterator is a kind of forward iterator, and a forward iterator is a kind of input iterator. And then finally we have random access iterators, which are the all-powerful, great ones that can do everything.
In constant time.
In constant time, indeed. So, some algorithms can only be called with certain categories of irritator? Irritator? Yes, probably after this.
That's my joke, right?
So, for example, standard sort you can only call with random access iterators. And other algorithms might only mandate a lower class of iterator, but if you supply them with a random access, then they'll do their work more efficiently. Because random access iterators give you a broader API. There's more things that you can do with a random access iterator than you can with a forward or with a bidirectional. So we'll go through them. Start with input iterators, which are rubbish. I'm not kidding, they are. So input iterators, the basic version is that they're something we can read from. So we can't necessarily write to an input iterator, but we can read from it. The trouble with input iterators, this is the really annoying thing about them, they're single pass, which means you can only dereference them once. And once you've done that, you can not do it again until you've advanced the iterator.
That's weird.
Yeah. So think of something like a stream, like a standard stream. So that's the example you're going to get in a second. Once you've read a value from a stream, you can't go backwards in a stream. So once you've read the value, it's gone. It's out there. You've extracted a value from it, you can't go back and get it again.
Consuming a buffer.
Consuming a buffer, yes, absolutely. So, good example is a standard iStream iterator. So this is a wrapper which lets you treat a standard iStream, so like cin or iString stream, or iStream as if it were a range, and use range-based algorithms or standard algorithms on it. Input iterators are a bit rubbish. but there are still lots of algorithms that work only on input iterators. So if you look at the documentation for any of their algorithms, it will tell you which iterator category it needs. This is just one I plucked out. There are lots. Standard counts. If you think about the implementation we saw for standard counts, we only read each value once. So input iterators are fine for that. We were just advancing, dereferencing till we got to the end, and then we stopped.
And they are used because they are more efficient, or to force you to think in a given way, or
they're used because input iterators you only use when you have to, right? So they're used because
to force you to think in a way. You can only use one, so you need to.
They have a defined semantic.
Yeah, okay.
Yeah, so for example, it's not possible to efficiently implement iStream iterator in a way that it's meets a higher iterator requirement. You could do it by copying values, I suppose, but it would be horrible. Output iterators are very similar to input. The only difference is that, oh, it's gone on 2 lines. Output iterators are ones that we can't necessarily read from. We're only sure we can write to them. And we do that, we say star iter, so we can dereference it. We say star iter equals value. So that with output iterators, the dereference goes on the left-hand side. When we're reading, it goes on the right-hand side.
Wouldn't that basically mean just to say that the operator star of that iterator class returns a non-const reference, and whether or not the thing it returns implements operator equals, you don't know?
Not quite, because the thing about output iterators is that they can return your proxy from operator star. No, that's one thing outputs are allowed to do. Yeah. So output iterators, again, they're single pass and therefore rubbish. But corresponding to iStream iterator is this thing, OStream iterator, so output stream, and you can wrap an output stream in this OStream iterator, and that only meets the output iterator requirements. So output iterators most often turn up, if you look at the standard algorithms, as out parameters. So standard copy, I haven't written it here, but standard copy takes 3 iterators as arguments. So a pair, denoting a range, that pair has to be input iterators, and it takes a third argument that's an output iterator. And what it does is it copies all the elements in the given range into this output iterator. And that only needs output iterators because it doesn't need to be multiple pass, it's just dereference the left-hand side and the right-hand side and copy one value into the other. So there are 3 categories left, higher categories. If they're writable, if they meet the requirements of an output iterator, we call them mutable. So a mutable iterator is sort of the opposite of a const iterator, right? Mutable and const being sort of opposites. Okay, now we'll get on to the good ones. So forward iterators have exactly the same requirements as, well, almost exactly the same requirements as input iterators, except we can read from them multiple times. So with pure input iterators, if you store an iterator, do something, and then later try and read the value from that iterator, you're going to get in trouble because the underlying container might have changed. With forward iterators, you can generally store the forward iterator or return it from a function, and absence of iterator invalidation because of the underlying container changing, it's okay to then read that forward iterator again. So a good example is this class forward list. So the standard forward list is a singly linked list, and it returns you when you ask what its iterator type is, it matches the forward iterator requirements. And there are a whole bunch of standard algorithms that require forward iterators. Again, I just pick one at random. So I guess most of the algorithms either require input or forward, and there are only a few that require the last two iterator types. And the last two are bidirectional iterators. So a bidirectional iterator is a forward iterator.
One before last.
Sorry?
One before last.
What did I say? Did I say the last? No, second last. Penultimate. So a forward iterator is a matches the input iteration requirements plus a bit more. Bidirectional iterator meets the forward iter requirements and a bit more. And the bit more in the case of bidirectional is that we can step backwards through the collection. Oh dear. This is supposed to be minus minus. My Macs tried to be really helpful and put an M dash in there, but it's supposed to be minus minus. So we can step backwards. So normally we say plus plus to advance forwards. Bidirectional iterators let you step backwards as well, a single step at a time. So standard list is a doubly linked list. So each node contains a back pointer, so we can efficiently step backwards. There are very few algorithms that actually require bidirectional iterators. I think this is one of only 4 or 5. I had to look quite hard to find one. Stable partition is one. And finally, we get onto the fun ones, random access iterators. So random access iterator is a bidirectional iterator, which we can advance by an arbitrary distance in constant time. And that in constant time bit is important. So what I mean by that is the length of time it takes doesn't depend on the number of elements in the container. So in theory, you can take any forward iterator and advance it n places just by calling plus plus it at n times, right? But if you imagine a linked list, if you've got 1 million elements and you want to get from there to there, you don't want to have to do this, because it's going to take a very, very long time. It's order n. Whereas for a vector, you can just go, okay, from that address, plus 1 million will get you this address, and that's fine. So random access iterators allow random access to the container, hence the name. So random access iterators give you a whole load of extra operators. So operator plus, I should have written it, but operator plus taking an integral value, I think a size t. Operator minus, so remember, random access iterators are bidirectional, so you have to be able to go backwards an arbitrary distance as well, so they have corresponding minus. Plus equals, minus equals. I apparently didn't write it, but you can also compare random access iterators. You can ask if one is less than another, which is something you can't do for bidirectional or below. So the best example is standard vector iterator. Standard vector is just lovely in every respect, really. It's the best example of everything in C++. Just when in doubt, use vector. It so happens, this was what we were talking about earlier, a raw pointer to an element of an array, a C array, also meets all the random access iterator requirements. So all this odd syntax, plus plus to advance it and star to dereference it, that is, we only use that syntax in order to allow pointers to meet the iterator requirements, which is kind of backwards, in my opinion, but there we are. Again, not very many algorithms in the standard library which actually require random access iterators. They're mostly the sorting operations, particularly the famous example is standard sort. There are other ones, stable sort, and a few others that I can't remember off the top of my head now. So, 5 categories of iterator. Which is sort of a lie, because if you look on CPP reference, they'll tell you that in C++ 17 there's a 6th one. One that's even better than random access, which is called contiguous iterators. But there's really, from a user point of view, no difference between a contiguous iterator and a random access iterator. It's really only of interest to people doing very hardcore library implementations.
I've seen 2 classes.
Sorry?
Us into classes.
Yeah, maybe. Well, it's only in 17, which we're not using for this class yet. Also, there's no iterator tag for them, so it's very hard to tell when you've got one. Oh, I'm nearly finished. I wanted to leave you some time to do this exercise, but talking too much. Oh, more tiny text. So, 5 categories. How do we know which category we've got? We know because the iterator has to tell you. Has to have a member type def called Iterator Category, and it has to be one of these 5 things. Standard input iterator tag, output iterator tag, forward, bidirectional, and random access. So this is mandatory. If an iterator doesn't have this, it doesn't qualify as a valid iterator. And if you want to retrieve an iterator types category tag, you have to use this horrible concoction: standard iterator traits, angle brackets, iterator type, colon, iterator category. It's ugly, I know.
So where do you specify the category?
Where? So it has to be, when you're defining the class, you can have a public member type. You can say, with modern syntax, using iterator category equals standard random access iterator tag, for example. And then other code can use this formulation to find out what your iterator category is.
That's going to be public.
Yes.
There is one message from ERA CPP about the continuous
iterators.
Yes, not quite continuous premise pointer like relative address guarantee. Random address doesn't guarantee elements are actually continuous. To be fair, I can think of a container in the standard lib that provides random access whose elements are not also continuous.
Yes. Yes. So this is just a note from somebody who's watching online who's correcting me about what the new contiguous iterator category allows. But the comment is that there aren't, or he or she doesn't think there are any containers in the standard library which are random access but not contiguous. I'm not sure about deck. Deck might be. I'm not sure off the top of my head. I'd have to look it up.
If the comment is not comfortable, we can always ignore it. That's the power. We can't hear them.
So why do you need to use the iterator category? Mostly you don't. This is pretty advanced. I'm just putting it here for kind of posterity for anybody who wants to read these notes later. There's a technique called tag dispatch, which is a way of selecting different implementations based on, or in this case, based on these tags. That's why these things are all called something tag. And this is what allows you to have a more efficient implementation for random access than you do for forward. Again, tag dispatch, unless you're doing really hardcore library programming, you probably don't need to care. This Iterator Traits class, it's actually got 5 member type defs, one of which is Iterator Category. The other important one is value type. And the value type tells you the type of the element that you will get when you dereference the iterator. Again, much less useful, or much less need for it in the C++11 world where we can just use auto. But if for any reason you wanted to get it, you can use this. You say standard iterator traits, brackets, iterator type, colon, value type, which is a mouthful, and that's why we love auto. So yes, 5 of them. Iterator category, value type, there's another one called difference type, another one called pointer, and another one called reference. I really wouldn't worry too much about those. It's mandatory to have them, but yeah. Last slide. Finally. So I said STL provides containers and algorithms. They interface using iterators. As well as that, it provides some other stuff, and some of the other stuff it provides are iterator adapters. There are quite a few of them. Probably the ones that are most useful are reverse iterator. So reverse iterator is a wrapper around an iterator, around a bidirectional iterator, and when you call plus plus on a reverse iterator, it does minus minus on its underlying iterator. And because the reverse iterator is itself bidirectional, if you call minus minus on the reverse, it will call plus plus on its underlying one. You say, well, what's the point of that? It's because there are certain standard algorithms that stop when they reach the first. So, for example, standard find will stop when it reaches the first, it finds the first instance of the value. And the reverse iterator allows you to start at the end and search backwards from the end of a container. So important that Vector and friends have these rbegin and rend methods which return you their iterator type wraps in a reverse iterator. And again, there are free function overloads and there are const versions, crbegin, crend. Probably even more useful than reverse iterator is something called a back insert iterator. And what this does, it's an output iterator. So it's not very powerful, but what it does is when you dereference it and assign to the dereference assigned to it, it calls pushback on its underlying container, which most often will be a vector, and it inserts that value into the back of the container. It's a back insert iterator. And this allows you to not have to know the size of the vector in advance when you use it as the output of a standard algorithm. Back insert iterator is very useful. Standard copy is probably the most used, but there are quite a few more. And next week we'll have a lot of examples. For example, copying all the unique elements from one vector to another. We're going to really go in depth into the algorithms next week. Finally, I find this quite useful. I guess it's quite an advanced one, but there's this thing called the move iterator, which is another wrapper, another adapter, another wrapper. And what it does is when you dereference it, it gives you an R value reference, the element, rather than an L value reference. So it's moved, the element is moved out of the container. And this can make certain algorithms more efficient. You just have to be quite careful about how you use it. But when you get a bit more, well, I don't know, maybe you guys already are. When you get in the hang of using the standard algorithms, you can look at using these adapters because there are some quite useful ones. Anyway, that was a lot of chatting. Time for you guys to do some typing. This is not, I will say, I started out thinking, hey, I'll set them as a challenge. This will be a useful learning exercise. And it's been quite a while since I implemented an iterator, and I realized that it's not actually all that easy to do because you've got to overload all these operators that we've already seen. But we're going to start off at the beginning, begin at the beginning, and we're going to gradually add more and more functionality until eventually we're going to end up, well, you probably won't in 45 minutes, to be honest, but eventually you can work up to writing a full-on random access iterator. So if you look at this URL on GitHub, you can clone a repository there, and
the idea is at the end we should resubmit our work to standard committee to replace the STL one.
No. This simplified vector is not very good. It's very basic. Racing towards me now. Okay, so I suppose most of you have done some of my exercises before. If you open this is a CMake project. If you open it in CLine or another CMake compatible IDE, other IDEs exist. You'll find there are, I think, 4 or 5 different targets in there. So start off, and they each test different requirements. So the first target just tests the basic iterator requirements, and then we have input, then forward, then bidirectional, and finally random access. Except the tests for random access don't actually exist yet because I ran out of time writing them. If you manage to write a random access iterator, you can write the test yourself. But these are not the simplified requirements that I have put on the screen. These are the full-on requirements as specified in the standard. I would highly recommend looking at the CPP reference links that tell you in absolute gory detail what is expected of your iterator type.
And feel free to ask for help.
Yeah. If you've got absolutely no idea how to get started, then put your hand up and we'll go around and
all right. Start with a constructor as my first piece of advice.
Yeah. You have no idea how to start. Okay. Are you logged into the Wi-Fi? Okay.
Yeah.
Okay. You both, this is your first time?
Yeah.
Wow. Okay. So we jumped into somewhere quite advanced.
Yeah.
Well. You haven't done the exercise yet. Okay, so if you go to that URL at the bottom.
It is. Go back to the elevators. Yeah. Actually, I'll have to open the door for you. Oh, sorry. Sorry.
So first things first, you have a C++ IDE. Any way of writing C++. Yeah, Visual Studio Code. Yeah. I'm not so sure. Yeah. So you're running Windows, aren't you? You've really come. We've been. It's like jumping in yes, as I say, week 21 of a.
Yeah.
So you've done pretty well to still be here, to be honest. I wouldn't have blamed you if you just left. I think.
You can implement it.
Are you any good with Linux? Okay, so we have Oliver has left, but when he comes back, we have a virtual machine which runs the Linux distribution. It has all of the developer tools already installed. So if you've got a way of running a VM, if you've got VMware there or something, VirtualBox, yeah, perfect. Then you can run this virtual machine. I can't remember the download link, so I'll have to ask Oliver against that.
I think it should be on the website.
But I don't know whether you're even connected to the internet. Okay, so you've joined it.
Yeah.
Okay, so. Okay. Yeah, so you've, as I say, jumped in right at the end of, and this is, as I said, not a trivial exercise. So if you're not familiar with C++ at all, what I would recommend actually is if you look in on the GitHub, you can just so you've got this course materials directory, and this has all our materials from previous weeks.
Oh, okay. But first of all, which will be enough to do the I can take the experience of starting from zero. The first 4 or 5 weeks of material.
Oh,
Big enough as well. Also, you praised me for that.
Thank you. So yeah, we have those are got exercises to go with them. So I would recommend, with if it's your first session, have a look through the sort of that material, and if you want to try some exercises, how we here because this is it.
Then something else.
I mean, if you want alternatives, I can get the teacher to stick it in an adjacent room.
And it's the same thing. So
No, don't worry. I wasn't complaining. But when I work, like when you go to the bakery, it's not like that. You go to.
Yeah. Okay. So if you go.
What?
And then there's this repository called course materials.
Have
In there you can see, this is section 21, but we have.
I think you gave me 4 or 3 times. I'll do it.
Read through, start on week 1. If you think that's already easy, just.
Did you go
week 2.
there?
There are lots of exercises in there as well. If you want to try them out. Awesome. Yeah, so you mostly do JavaScript, did you say, or did you? I can't remember.
Remember it was Python, but JavaScript is around.
So you're a relative newcomer to C++. 2 weeks. A few weeks. Just from this class.
That's like the one you mentioned to you.
Yeah, you need
What is your event and what are you with the would you trust that someone who learns a lot of martial arts than just reading books? It's the same sort of
Oh yeah, you need to on YouTube.
Sure, unmuted.
Yeah.
And we are back with sound.
Hello again. People are busy trying to get on with this rather challenging exercise, so we muted the sound.
We want to avoid you
rather than hearing everybody's bad language.
You. Oh.
Okay. So if you try and compile, if you run the basic iterator test.
No, you want operator plus.
This one, yes.
Yeah.
Well, I guess he doesn't. You don't test operator plus or minus, do you?
Oh no! What have I done?
No. So.
Oh crap! All right.
Dark magic.
Sorry.
No worries. You know, I wish I could.
I'm going to fix that right now.
I wish I could do such a mistake.
No, I'm not sure you have to do a separate one. But also, why it's const accessible? That's strictly correct.
Surprisingly, there's nothing happening on the Twitter.
Yeah.
Nothing. Zero.
Yeah.
Well, I changed it to mute.
Yeah, I don't think that's correct.
Okay.
Because you shouldn't be allowing. You shouldn't be allowing to increment a const instance of the. Well. That's a question. Tristan.
Yes.
On an iterator, the type of the iterator is declared const. So I get begin, and I quantify it as to a const ref. And I can't call plus plus on it anymore, can I?
No, because plus plus mutates the iterator itself.
Yeah, because he declares the build as mutable to be able to modify it from const instance.
Oh right, yes, that's cheating somewhat, yes.
Yeah, your operator plus plus shouldn't be const accessible. If it's const, you shouldn't be able to. I mean, what you've done there obviously compiles because you made it mutable. Right. But you shouldn't make it const accessible feature. Yeah. No, it's not cheating. You pass all the tests. Right. I can guarantee that none of his tests are going to use a const anyway. Oh, right. So if you make it non-const, it'll still work. Oh, right. Also, you should only want. You don't need a separate operator plus for pre-increment code, do you? No way. Expressing that way. There's no separate operator implementation for pre and post.
Yeah.
Oh, one takes an in, doesn't it?
Yeah.
I mean, is a forward iterator bidirectional iterator?
No, the other way around. Bidirectional is forward. Yeah.
Yeah. As in, bi-directional, two directional, yeah.
Yeah.
Sorry, what does your test require? Well, multiple tests.
Yeah. So there are four or five different executions. Yeah. Okay, if you're trying to build it with GCC and you're seeing errors about underscore is swappable, then that was a mistake on my part. So I've just updated the repo. So if you're seeing that error, then I've already corrected yours, Tom. But you can
Thank you.
Do a git pull, and it should bring you that update.
I don't know. I can't read it. Hold on. I need to get a microscope so I can read it. Dear Lord, no, because incrementing the element already increments it to the next piece. You have a pointer to an int, right? And an int is 4 bytes. Int plus 1 doesn't go up 1 byte.
Is there a command to run all the tests automatically?
No, because the type of the element is already t, so you're going to increment it by a stupid amount. You can skip element. Look at the type of element.
So there are 4 or 5 different targets. So if you skip right to the last one, which is bidirectional because I didn't get around to finishing the random access test, then it will execute all the previous level tests as well.
It's going to do elements plus plus or plus plus element.
So there are, I think, 4 or 5 different executables in there: test basic, iterator, test input, iterator, etc.
Goes to the next element. You can either stick it out the size for you and goes to the correct memory address. I mean, the point is it doesn't matter.
Yeah, don't do that.
And you're transferring down 5%.
I am on 30%. And I'm still streaming.
Just a question. We were talking about the const, but const with respect to iterator is based on the value it's pointing to, not the actual.
Yeah, but your iterator itself shouldn't be const, right? So you can have a const iterator, and it doesn't mean the iterator type is const type. It means that it's literally a type. Like const underscore this thing. It doesn't mean it's actually a const instance of the iterator itself. So imagine you have an iterator type, right? T, okay, and T will give you access to elements of the container as not const, so you can mutate them. Then, so that's dot begin, for example. Then you have dot c begin, which returns a different iterator type, and this iterator type is still mutable. It's still not const, so that is like you have maybe t and const underscore t.
Oh, it's
not using the const keyword, so it returns this other iterator type, which inside the class implementation of that particular type of iterator says, I'm never going to allow you to access the elements as non-const.
The people want me to return a vector iterator end. A vector iterator end. Not do things good. If I just return
a pre-increment operator.
No, once the operator plus plus.
Yeah, that's
returning a vector iterator.
That's a and yes, that's a pre-increment operator. Operator plus plus int as an argument is the proposed. Yeah, well, because it increments itself first, so now it's pointing to that, then it just returns a rep. Operator plus plus has to return. Oh, sorry, operator plus plus int. Operator plus plus from int, that single argument is proposed increment.
Okay. So I can't just copy the structure.
You don't need to capture the argument.
Well, it's not really empty. It can also be T. Operator plus T.
No, T.
Is it always?
It's just BS argument, totally different. But you don't want to read it. Don't try and read it. We'll try it.
I can just
The in parameter is a dummy parameter used to differentiate between prefix and postfix versions of operators.
this is legal. First element return dereference this pointer. Yeah.
You'll put each of the posters. Auto ret equals star this. Someone's return. Auto ret equals star this. Increment the element. Return ret.
Something to what just copying the string.
Or you could just actually return a decal point start there. Ignition. Your post-fixing operator construct a new instance of itself.
Yeah,
right. And you can do all of the line out.
Oh, okay, you're gone. Okay, so I didn't mention this in standard iterator. That was a helper class that was in early versions of C++2, and it would define type tests for you, which is great. Like, for some reason they deprecated it in C++. Yeah, it's going to the iterator, that's why I didn't mention it. But it's fine because you've done this pretty good.
Like constructing a new one.
Okay, yeah. So what you're saying is this function is okay to call on a constant. So this one I was writing up here for you. So the difference between an iterator and
but again, it's for maintenance.
Okay, so in this case, you said also equal vector begin.
I mean, you can really make it one, never touch it again anyway.
So vector begin returns you a mutable iterator.
No, you want a post increment element, not a post.
So if one is
how you can return
vector iterator,
post increment value.
And if one is non-constant,
It's before
so we can call taking operations on the difference between the iterator itself being constant and the thing it points to being constant.
other key should be put on the
So in this case, we can have
On the list
the
this time.
same except we declare the iterator as constant or
Fine. I'm fine. It's no problem. Done deal.
Now, if you think about what it means for a type to be constant, it means we can't mutate it in any way. And calling operator plus mutates the internal state of the iterator. Right? So
Can you
the correct thing to do is to remove the constant.
you set it to the screen.
Yeah.
Oh, you did.
Well, that's unfortunate terminology, because that is what the name const iterator, because iterator to const, I suppose, would be a better name. Iterator to const, but for whatever reason we call them const iterators, which is an unfortunate name, because you're absolutely right, because just remove the constant if you just, so make those member functions non-constant member functions, and you'll be fine, yeah.
Getting this thing to focus on stuff is
Well, it doesn't help if I keep walking in front of it.
not fun. I don't think you sort of really it's even when you do stand in front of it, it sort of figures itself out better. Like
Just doesn't like
quite How is it looking on the screen? I don't know.
I think the YouTube quality, double encoding is going to be great.
Yeah, that's the thing.
Maybe take a photo and put a photo.
I think one of the guys in our company was complaining. Oh, sorry.
Yeah.
No, it's a harmless thing. No, he's just complaining about country code.
How would you handle trade into problem?
That's what it is.
All right. The tests that are coming online, the tests don't seem to be exhaustive. No, there are no random access iterator tests, mainly because I ran out of time before the class, and I didn't think these guys would have enough time to get as far as random access iterator tests, and I thought I'd get away with it. I didn't bank on people online racing through all the requirements. So I will add them to the repository without there at the moment.
Teach people what you need to do.
The mutable keyword?
Yeah.
Oh, I'm not sure that's going to come up actually.
That's what I say. I was mildly impressed that you came up with it just out of the fact that you knew that you could do that.
He's always trying to get it.
Well, no, you weren't. The thing is, you weren't really cheating because it shouldn't matter. It should not.
No, well, I'm very impressed you used that standard iterator thing because, as I say, it's been deprecated, so I didn't.
Does it show my age or something?
C++ old timer, is that what you're saying?
Well, no. Oldie.
The actual location of the actual value.
You need to implement operators with equals. Yeah, so just compare elements, they're pointed about.
The location where the point is not the actual value in them.
Correct.
And for what we can look at just use as to the split.
Well, yeah, you can't compare that. End is past the valid end, so you can never do that.
Whoa! Can you read that?
No. I try my best.
So where did you get it?
Alright, nice.
Yeah.
Oh, yeah, that's a nice way of doing it. Yeah.
Well, I spoke to him about that, because I said you could just do constructor. I said for maintenance, the problem shite. Because someone adds another field and wants to change behavior, because you're not using the copy constructor, it's going to suck. But otherwise, yeah.
You haven't tried compiling it, have you? No. Because because I'm in the habit of naming my member variables with a trading underscore. You're going to. I mean, you must have the best size file in the world.
No, this is just.
We're wearing glasses and all.
This is just using. I don't want to.
No, it's just
for 1 second.
That's mine.
Want to mess around with my.
Have you got Office Lens?
Yeah. Yeah, so it's probably an annoying habit for anybody who isn't me, but in the habit of putting in a trading underscore on my member variable name. Sorry?
I mean, technically it would, unless you get the job with a standard library implementer. Oh, isn't it always
or lowercase, I believe, banned in the global namespace is okay. Another namespace.
Yeah.
Technically, according to POSIX, anything underscore T is banned in the global namespace.
I use namespaces of my own then.
Just a question.
Semi-static analyzer. Semi-static, right? Analyze the source code. one thing to complain about is and it's sort of capital letter. It says a code smell.
It's just a matter of
style. An even better one, switch case. Oh yeah, I've got two good ones. Switch case. You don't have a default case. I don't want a default case. I want a warning to be emitted if we change to enum and there's not.
If it's not exhaustive.
Yeah, I want it to not do something right.
Well, you could have default and then a certain of which.
Yeah, that's true. Actually, yeah, that's not a bad idea. I like that. All right, no, I'm doing tomorrow. And then the other one was this one baffles me. Explicit return types on landers. Bad. Yes, according to this thing. What? And additionally, the reason we have these explicit return types is because the lander doesn't actually do anything except throws the exception.
Okay.
It doesn't return anything. So you have to have that return type in order to conform to what the core is.
Return value.
No, if you have arrow type. So you have like square brackets, parentheses, arrow type, and then in the body of the function it just throws.
Yeah, but what I mean is what type do you use if it never?
So you don't have to. If you throw, but if the ultimate
statement in the declaration of the lander, you say arrow something. What's the something?
Oh yeah, so the something is what the thing that's going to call it expected to be. Not actually a necessary function, but in something similar. So it's expected to have type.
I turn my head sideways. So let me write that in red text.
I thought you were going to say Rust for a second.
Rewrite it in Rust. Yeah, all this problem with dangling iterators that just go away. If only we write everything in Rust.
Yeah.
Yeah. Just Rust London University.
Yeah, no, Lord, no.
Just a question. What if the container is like a tree? Can you still use it?
You mean a B tree?
Yeah. Yeah, so then you've got an interesting choice to make. Because do you want iteration to go step first or breadth first, or how do you want to traverse the tree? There are multiple ways to traverse the tree.
Yeah, but with the interface like plus, plus, and minus, minus still makes sense.
Yeah, I mean, the thing is, so a good example of this, maybe not of trees though, is say unordered map or unordered set. So obviously a hash. You can obviously go through it just fine, but there is no ordering. Whenever you modify it, if you go and iterate all over it again, it's probably going to be in a completely different order. So it just matters about what do you care about. For a tree, you should still be able to. You can iterate it predictably. Stood max is effectively a B tree, and if you add an element, unless you explicitly insert it somewhere, then the ordering is preserved. So you can keep on iterating on that, and it'll always come out in the same order, plus whatever you added or minus whatever you removed. But in terms of how that's physically implemented in the standard library, I have the suspicion they use some additional memory to track that. Well, that's what I know.
What's up? You're recording a stream.
No, he's. Well, I say he is. YouTube is basically recording it for us.
Okay. I just wanted to say, I was hoping to stop out 20 minutes when we're reading. It's happening because the start of the course.
I still have them. And actually, I will just give them to you because things are a little bit more cool. I'll show you. I'll just give them to you. They're pretty good. Yeah, I post it. It wasn't a lady one. Gaming one as well.
So we can say where we are. Live on the internet, we can say people.
So yeah, so happily, when plus London University, we just put the Minecraft is fine. Go city point building.
Can't we just go look for the other company on the other side?
Well, it's very because we're not affiliated with them.
Yeah, but we can say don't look at the other, not the side for the fucking look for the other one.
Okay, guys.
Oh, you mean the wrong side?
2 minutes to 9, so about time we wrapped up, I guess. So thank you for coming, especially to the two new guys. Sorry for dumping you in.
The deep end.
Literally, you know, the deep end. But as Tom said, we're planning on beginning again from the beginning in May. Is it, Tom?
Yes, the beginning of May. The idea is to do it in the beginning of May. But before that, we will, for those who are more experienced, we will do our best to run a test for you, to torture you, to ensure that you actually have the knowledge. But for the newcomers, basically spread the word, because from the 1st of May, we want to start a slightly newer version of the course based on one of the books.
So you can communicate, they can tell to many.
Yeah. I mean, the beginning of May, so first Tuesday of May, whatever it is.
Okay.
And then obviously we will go through skills matters. We will try to stay there as long as we can, although some of the sponsors are trying to pull us to their offices, which obviously we don't want to go.
Potential sponsors.
Yeah, potential. So that's the reason we're looking for sponsors. So if you know any company that is willing to help us, let us know, so we'll have a balanced, approach. And obviously feedback, I need feedback from you. As well, if you can send me photo with your quotes, what our group is giving you, that will be amazing. Now, we're going to pub. I will have to run out because I got a message from my wife that she unfortunately needs to go to emergency room, so I'll have to shoot off. So I'll leave you today. I'm sorry I won't be on the pub, but I leave you in capable hands.
Yeah.
So look after our guys.
I rushed off, unfortunately, but Ollie and I hope Justin as well, we're going to the pub. So you're welcome to. I think I know someone who's coming along.
I don't know, unfortunately I'll have to pass. I've got early start tomorrow, so great.
What's early start? God, that's not early start.
Okay, so there's Peter and BNS, so if you want to take something home, grab it.
Okay, are we off?
Next time.
Also, for those of you who did just join us, don't be scared off. We're going to be doing algorithms next week, so if you have any math knowledge, you'll find it useful anyway. And then after that, we have Phil Nash coming in, who's going to be discussing a framework he wrote called Catch, which is basically something that enables you to very easily write unit tests. So, code to test your actual implementation code, and it enables you to spit out, fancy reports to say if everything passed or what failed and all that kind of stuff. So if you have like a build system like Jenkins, then it can pass the XML and give you a little web interface that says this failed, this didn't. So he's going to cover that. And then I believe the week after that, Tom, we're going to do a
We'll have revision. All of these, if you go to our website, in the latest blog post, I put all the stuff, the things which we'll cover for next couple of weeks until the new course will start. So be very welcome. Go there, make your go-to thing to find out about all the information. Blog is where we put all the latest updates. Yeah, you have our website.
Yeah.